Here I'd like to highlight our first big named theorem, the squeeze theorem. Generally, my rule of thumb is if a theorem is named, I think that one is worth knowing. That one is worth really taking a look at, because I will probably ask you on, say, a quiz or an exam about the squeeze theorem or about that named theorem. So let's talk about this one. It's a little bit it's hard to understand, but as soon as you draw a picture, I think it all of a sudden makes a lot of sense. So here it says, suppose we have three functions, f of x, which is less than or equal to g of x, which is less than or equal to h of x, for all values of x near a, except possibly at a. If the limit as x approaches a of f of x equals the limit as x approaches a of h of x equals some L, then the limit as x approaches a of g of x is also equal to L. So this one's pretty tricky. There's actually a lot going on here. So I think for here, it's most helpful to draw a picture. So here you've got three functions, and I'm going to try and use different colors here. Let's draw a coordinate axis. You know what? We'll leave it. That's fine. There we go. Okay. So I'm going to pick three functions here. I'm going to say f of x, I'm going to do that one in blue, is the least, so it's the smallest. If you want to think about it, I almost think about it as like the floor. So okay, here, let's say here at a, we've got some limit. We'll make it a parabola here just to simplify things a little bit. Perhaps it looks something like this. And then you've got this other function, which I'm going to draw as h of x here. This is kind of the ceiling. This function is bigger than all of the other functions. I'm skipping over g of x because I'm going to come back to that one. So actually, let's think about what I know here about f of x before I start talking about h. Here we said that the limit as x approaches a of f of x is equal to L. So we know that this limit right here, this is L. And I also know that the limit as x approaches a of h of x is also equal to L. So I have to kind of pass through that same point. Maybe I pass through it, maybe I don't, but in either case, that's the value of my limit. And it might look something like this, right? It doesn't even necessarily have to. You could do all sorts of crazy oscillations and things like that, but we'll just draw it like a parabola here just for the sake of simplicity. So what happens here? What do we know? We have this third function that we haven't talked about yet. This is called g of x right here. G of x lies between f and h for all values near a except possibly at a. So again, that's just saying the behavior exactly at a, we may not know what it's like, but for all other values, if you get close to it, it lies between f of x, which is right here, and h of x, which is up here. And I know that these two, because of the way I've constructed it, these two functions approach the same limit. So if you think about it, if I come from, let's just start thinking about the left-hand side. I'm going to draw g of x, and I'm going to draw it as big as I possibly can, right? I've got this weird oscillating function, right? Perhaps it looks something like this, but it can't go higher than h of x. It's always less than, okay? So maybe it goes back down. Oops. And then, okay, well, it can't go below f of x, so okay, it's got to go back down. It's trapped in between these two functions, so what happens? Well, it gets smaller and smaller and smaller. There's nowhere for it to go other than that same limit of L over here, which is what we said over here. Same thing on the other side, right? If you drew g of x over here, again, you can draw it as tall as you want, but it can't pass h of x as you get close, and it can't pass f of x. It's stuck between these two functions. So there's nowhere else for it to go except for L as you get closer. Now, maybe there's a hole there or something, but remember, holes don't tell the whole story. They tell you about the value of the function, but what they don't tell you about is the value of the limit. So there's nowhere for this function to go other than this point right here, which we said, hey, over there is L. So this is, I think, once you draw it out, it's a very intuitive theorem. It's a very powerful theorem. Like, oh yeah, that does make a lot of sense here. So I'm just going to show one quick example here using the squeeze theorem. So here I want to use the squeeze theorem to show that the limit as x approaches 0 of x squared times sine of 1 over x is also equal to 0. So here I'm just telling you what the limit is. I'm telling you this is the limit. You have to now show me that this is in fact the limit. Prove to me in a way that this is in fact the limit. So I'm going to start off with sine of x. I know that sine of x, I'm just trying to find something simpler to work with here right now. Sine of x always lies between -1 and +1. It's always stuck between those two, right? So -1 is less than or equal to sine of x is less than or equal to +1. Hopefully we remember from trigonometry, right? We drew this oscillating function. It looks something like this. Hits +1 down up there, hits -1 down here. It's stuck between those two values. And really, you can plug whatever you want in for sine of x. It's always going to be bounded between -1 and +1. So I can also switch this sine, or rather the inside part of my sine function, to say -1 is less than or equal to sine of x is less, sine of 1 over x, excuse me, didn't fix that. Sine of 1 over x is less than or equal to +1. So okay, I've got a lot of my function right here. I have this piece right here, but I'm missing that x squared. So here's what I'm going to do. I'm going to take this whole thing and I'm going to multiply every piece of it by x squared. So I'm going to multiply it here, I'm going to multiply it here, and I'm going to multiply it over here. So I'll have opposite x squared less than or equal to x squared times sine of 1 over x is less than or equal to x squared here. So I've now found these two functions, right? If I think about the squeeze theorem, the beginning of the squeeze theorem I think is the most important part. It says you have this function which is trapped between an upper function and a lower function. It's stuck between these two. So what I want to show then is I hopefully ended up with two easier to work with functions for my upper function and my lower function. So what I'm going to do is I'm just going to look at the limit as x approaches 0, because I'm pulling that from here. I'm going to look at the limit as x approaches 0 for both of these two functions. So let's see, limit as x approaches 0 of opposite x squared. Here this is opposite of 0 squared, so opposite 0, well, that's still just 0. So there's my kind of lower function. Now I'm going to look at the limit of my upper function, limit as x approaches 0, this time of positive x squared. So here 0 squared, 0 times 0 is 0. So I've now shown that, hey, the limit of that lower function, this guy right here, that's 0. The limit of our upper function, x squared, that's also 0. Therefore, by the squeeze theorem, this middle piece right here, therefore by the squeeze theorem, I've now shown that the limit as x approaches 0 of x squared times sine of 1 over x must also be 0 here. I have now used the squeeze theorem to prove this limit. So the types of questions I like to ask on, say, a quiz or an exam is I'll give you this inequality right here. I'll give you your upper and your lower function. And you then need to go and show me, okay, using this upper and lower function, find the limit of this upper and lower function, and then knowing that that middle function is trapped between the two, it must also converge to that same limit. So I would definitely take a look at these. I would definitely look at some other videos of the squeeze theorem, because it is probably the biggest theorem in this first chapter here.